So let's start by identifying a lot of problems I've been seeing. The problems I've been seeing is specifically relating to when do we use differential and when do we use integrated. Okay, we know kinetics is all about the rate of the reaction. There are two ways to study rate, differentially or using the integrated way. So our differential rate law, this is when we write this rate law. Rate equals, okay, whatever substance A is to its order, whatever substance B is to its order. Okay. Anytime you are told to write a rate law, we mean this. Okay. You're never going to be told to write the rate law, meaning the integrated rate law, because the integrated rate law doesn't give the orders for each substance. It doesn't have anything in there that you would need except for the constant. So we'll use our integrated rate law to calculate K when it's an applicable lab that would use integrated. But generally, and always when it asks for rate law, it wants you to write this. Rate equals this. So anytime you're ever asked to write the rate law, you're writing one of these. Now, when we use the differential rate law, the type of lab we use then is when different concentrations in different trials. Generally, we're going to use this lab when we can't see a change in concentration over time. Okay? We need to just keep doing the lab several times to compare using different concentrations. We'll hold something constant, we'll change something else. So we compare a change in concentration versus the rate to determine the order. Okay, so real quickly, another one of these examples. If that's held constant, I can look at what happens to H2. When that doubles. So 2 to the something equals 2, well 2 to the first. So that means that H2 is first order. Then I look at my NO. Well, I look for a time. Yay, H2 is held constant. I look here. When that doubles, this quadruples. So 2 to the something equals my rate change of 4. 2 to the second power would equal my rate change of 4, so this would be second order. If I were to write my rate law from this, I would say rate equals K. Instead of A, since I actually have a substance, I'd put NO. My order is 2. Then H2 for my second substance, order is 1. Integrated rate law is an entirely different type of lab. We have a different rate law for each of our orders. Remember, the difference between a 0 order and a first order rate law is just get rid of the ln, okay? Because it's the same thing as looking at their graphs. A change in concentration is integrated into one experiment over time. Okay, so we do this one experiment and we watch this change over time. We've done this lab several times now. We did it with the M&Ms. We stopped and measured concentration at certain times. We did it with our spectrometer. We watched it. We literally could watch this concentration change. As that absorbance changed, that means the molecules inside there changed. The refraction was changing. The wavelengths we were measuring were changing. So in these, we compare our slope of our 3 graphs to determine the order. Time versus concentration, time versus ln of concentration, time versus 1 over concentration. A quick key is if time is a factor in the question, if time is a factor at all in the lab, this must be an integrated rate law. Notice we're not using time when we do our differential rate law. The next problem I've seen lots of people struggle with is what to do when the other substances are not held constant. So I've got a trick for you with this. So if I'm trying to find the order of each one of these, well, now I have 3 substances, A, B, and C, and I look for a time when both of the other ones are held constant. So if I want to look for a change in BR, that's held constant and that's held constant. Sweet. Constant, constant, look at this change. That's a change in 2. That's a change in 2. So 2 to the something equals 2. That's 2 to the first. So that's first order. To do the next one, I look again. Is there a time when the other 2 are held constant? Well, yes, here and here and here and here, they're held constant, so I'm looking for the change here. This is a change of 1.5. This is a change of 1.5. 1.5 to the something equals 1.5. Once again, it's first order. Now to find the last one, I have both of these orders. I know the effect of both of these, but there isn't a time when both of these are held constant for me. So what I need to do, I have to see a change here, and I need to compare and account for the fact that I already know both of these are first order. So very quickly, I can pick one, how about going from here to here. Okay. The reason why I chose this one, you could pick any. The reason why I chose this one is in this case, A would be still held constant, B changes. But I'm going to look at all of them. So this one is being multiplied by 1. 1 to the, I know it's first order already, so 1 to the first order. This one is being multiplied by 3. 3, I already know it's first order, 3 to the 1. This one is being multiplied by 2. 2, this is the order I'm trying to find. And I put this into effect. And this, you plug it into your calculator to figure this out. It's being multiplied by 12. So now we logically solve for what is my missing order. 1 to the 1 is 1. So 1 times 3 to the 1 is 3. 1 times 3, so I'm at 3. 3 times 2 to the something equals 12. 3 times 2 squared equals 12. That makes this one second order. Now we technically could have done this method for all of them once we know the order of the other ones. Because when these were being held constant on this first one, I was saying, well, that's being multiplied by 1, that one's being multiplied by 1. B and C were both being multiplied by 1. That doesn't affect anything. That's why we were looking for them being constant. If it's not changing, it doesn't matter what the order is. This could have been 100th order. 1 to the 100 is still 1 and won't affect the reaction rate. Now this question was originally part of your lab. I took it out so that way we could go over it in class. In a lab, the orders of two reactants, A and B, were determined experimentally to be 2 and 3 respectively. The rate law for this reaction, write it. Well, anytime you're asked to write a rate law, it's always the same. Rate equals little k. If you put a capital, you'll miss it. Little k. Concentration of A, all I have is A and B, so I'm actually going to write A and B. If you have a substance, don't put A and B. Actually put what the substance is. A and B, and my orders are 2 and 3. What is the overall order? Well, 2 plus 3. I add them together to get my overall order, so my overall order is 5. So 2 plus 3 equals 5. Now, what would happen to the rate if A were doubled? Well, let's think about it in terms of what we just did on the previous. If I had a data table here, and I multiplied this by 2, and I know it's second order, what would happen to the rate? It'd be 4, right? It would quadruple. Okay, so whatever your change is in here will equal that. It said, we didn't say we changed the other one. It said we kept the other one constant, so it'd be times 1 to the third order, which still wouldn't affect anything. What would happen if B were doubled? Well, if I keep A constant, so it's still 1 squared. I haven't changed, I haven't multiplied A at all. A is being multiplied by 1 times, now I've doubled B. Okay, now B is third order. So what would happen to my rate? Well, 1 whatever times 2 cubed would equal 8. The rate gets multiplied by 8. And what would happen, finally, if both A and B were doubled? Okay, well, A is doubled, and it's second order, times B is doubled, and it's third order. So that's 4 times 8. My total rate would be multiplied by 32. I'm going to do the very last AP question with you. It's the very end of your packet. Decomposition of gas X to produce gases Y and Z is represented by the equation B above. In a certain experiment, the reaction took place in a 5-liter flask at 428 K. Well, I'm given temperature a lot. I'm going to underline it just in case, but with kinetics, they're just telling us it all occurred at one temperature. If we didn't say it occurred at one temperature, then that could mean varying temperatures, which would have a massive effect on rate. But this 5 liters, we might need that. We might not. Could be total nonsense, don't need it at all, but we might need it. If they're giving us numbers, let's make sure we indicate that we might need it. Data from this experiment was used to produce the information in the table below, which is plotted in the graphs that follow. I have the graphs on your page, not on mine. So my first question is, how many moles of X were initially in the flask? So initially in the flask, you should know to look here at time 0. That's when I started. And when I first started, here is my molarity. It's asking for moles. Well, molarity is moles per liter, and, well, that liters actually does something. That's our simple intro point. Okay, if I have 5 liters, and I have a molarity of moles per liter, that gives me 0.0317 moles to begin with. Okay, for my next question, how many molecules of Y were produced in the first 20 minutes? So that means starting here, I went 20 minutes, so I'm here, and I'm looking at my molecules of Y produced. Well, the number of molecules of Y produced is going to be determined by how many molecules of X were used. So if we see how many molecules of X we started with, we can do our mole ratio. For every one of these that's used up, we produce 2 of these. So however many molecules disappeared in these 20 seconds, twice that many Y's appeared in that 20 minutes, not seconds, in that 20 minutes. So to apply this, I'll see my change in molarities, and they're both moles per liter, so I can just look at my change in moles here. 0.00427 minus what I originally, or final minus initials, what I started with. So I have 0.00206 moles of X were used. Okay, that's how much has disappeared in this time. Now, for each time we lost a mole, or every time we lost even one individual, we produced 2. So for every mole of this that's used up, I produce 2 moles of this. So I'm not done with this problem yet because it's asking for molecules of Y. So I use stoichiometry. If I have this many moles of X, how many molecules of Y? Okay, moles of X, I have a 1:2 ratio. For every 1 mole of Y, MC is my shortening for molecule. If I have 1 mole of Y, times 6.02 times 10 to the 23rd molecules per mole, 2.48 times 10 to the 21 molecules of Y. Next, what is the order of this reaction with respect to X? Justify your answer. Now this is when that whole question of differential versus integrated comes into play. If this was differential, then we would do what we've been doing. Look at change in what happened to your concentration, look at the change in what happened to your rate. Notice I don't even have a column for rate here. I have time. If time is ever a factor, we're talking about integrated. Integrated rate law is when we use these 3 graphs. That one, and this one. Oh, they already graphed it for you. If they wanted to be really evil and make you calculate slope, they could, but they don't. They gave you the graphs. You look at the graphs. Based off of those 3 graphs, we have a straight line at ln of concentration versus time, which means it's first order. Now it says to justify your answer. That is your justification. The reaction is first order because a graph of ln of x versus time yields a straight line. Write the rate law for this reaction.
That's dedicated.
Rate equals K, X. We already said it's first order. So hard. Next question. Calculate the specific rate constant for this reaction and specify units. Remember, I gave you that little hint on how to do that. I promise you there's points on your test tomorrow, and I promise you there'll be points on the AP test to specify units of K. Now, how are we going to calculate K? This is actually where they tried to trick you. They made you write a differential rate law. But you don't have the information to use this differential rate law to solve for K. What you have is information to solve using integrated rate law. You did an integrated rate law lab, therefore you have to solve for K using integrated rate law. We said it's first order. You need to know what the first order integrated rate law is, what that equation is, and it's given to you. You just need to know which one it is. Then you need to know how to plug things in. If you're solving for K, you already know you have a straight line, so you could pick any 2 points. You do an original concentration. We already know what our original concentration is. That was at our time 0. You pick a point. It's a K. It's a constant. Whichever point you pick, you'll solve for the correct K. Make sure you put the right units. Okay. If it's first order overall, which it is here, right, of 1 here, first order overall, if you use your little hint, L is N minus 1 over moles N minus 1 per time. Per time, which in this case was minutes. Well, my overall order was 1, so L to the 0, right? 1 minus 1 is 0 is 1. So I have 1 over moles to the N minus 0. 1 minus 1 is 0, so moles is still 1 per minute. My unit is just per minute. Can also be written like this. Got to be able to use this little trick for your units.